Fractal principle. The sum of the sides of a polygon is slightly greater than the value of its perimeter, because when adding, we always add twice the vertices or points of connection of each side. See drawing. Postulate 1. All of this is due to the characteristics of the dimensional structure of non-Euclidean space. See my work on dimensional geometry, which tells us that there is no such thing as a zero space point, or point of no value, but rather a real dimensional point, even if it has an infinitesimal value of space. And so, we can imaginatively cut or join two segments of the same line, without losing or gaining space, but we cannot join two lines at an angle, since for the lines to be joined, their endpoints or coincident points must be common to form the complete figure. That is, either they overlap, and the figure is completed, as we see in the explanatory drawing, or there is an empty point at the ends, and the figure is not fully constructed. But moving away from this theoretical preamble, what interests us is the aforementioned fractal principle. The sum of the sides of a polygon is slightly greater than the value of its perimeter, because when adding, we always add twice the vertices or points of union of each side. And this applied to the adjustment of pi by adding the sides of polygons inscribed or circumscribed to the circumference. According to Archimedes, it would lead us to the conclusion that the number pi thus obtained must be slightly greater than the true value of pi. That is, if we add the sides of inscribed polygons of a quasi-infinite polygon, the result will be that the value obtained will be slightly greater than what the true pi should actually be. How much greater? Well, it seems that the cut or coincidence can occur in a polygon with around 4090 sides, but of course, that would have to be adjusted better than I have done. And the same flaw or defect seems to be present in series. If they represent the transformation of curvatures into straight lines, then they will follow the same principles of union and geometric structuring that we mentioned before. Postulate 2. On the other hand, and referring to my work on dimensional geometry, one of the consequences of curvature is that when a straight line bends and becomes a curve, said straight line loses dimension. On the inner side of the curve, all its points are now closer together and therefore have lost relative distance, which the entire straight line must have also lost. That is to say, the more we bend a straight line, the greater its loss of dimension. Conversely, when we straighten or extend a curve or circle, the result will be a gain in dimension in the resulting straight line. Now, referring to the true value of pi, I understand that I have already written and published quite a bit about this, and they are in these accompanying drawings. The number pi should be obtained by a direct function of the only parameter we know about the circle with respect to pi, which is the value of the diameter of the unit circle with radius 1 and diameter 2. That is, 2 is the only known value that should lead us to pi. Of course, the values of the inscribed and circumscribed squares of the circle are also functions of 2. However, playing with the value of the diameter 2, and using the Pythagorean theorem with the inscribed and circumscribed squares, and their right triangles, we can find the appropriate powers and roots to find the correct number pi. As we can see, the lowest power of pi that connects us to the diameter of the circle and to the sides of the inscribed and circumscribed squares is the number 17. That is, with the 17th power of pi, we can connect with the power of 2 and powers of the inscribed and circumscribed squares of the circle. Even with the other magic number, that is the number phi. But as I've already said, there's a lot written and published on the subject, so I'll show you drawings that show all these principles and adjustments for pi. Thank you very much, friends.